Hey you guys, this is Unit 3, Notes number 6, Linear Approximation, okay? We're pretty much wrapping up the unit, so stay patient, okay? So this right here is called Linear Approximation. Um, just to give you guys a little bit of insight, okay? This is kind of like an introduction to what you're going to see in Calculus BC. So here's something to think about. When you type in your calculator, 5 times 4, it'll spit out 20, right? But really what's happening is at a very fast rate, the calculator is programmed to adding 5 4 different times at a very fast rate, okay? A calculator knows only how to add, subtract, multiply, and divide, right? But really just add and subtract. So I want you guys to think about this. When you're telling the calculator the square root of 9, it'll spit out 3, but what exactly happens in between? Okay? Now, some of you may be guessing, well, they're thinking of two numbers that multiply by itself that'll give you 9. Okay? So, they might think, okay, 1 times 1, that's definitely not 9. 2 times 2, that's definitely not 9. 3 times 3, that is 9. So then they're going to spit out 3. So the thing here is the calculator is not that smart. And actually, to program a calculator to do this at a very fast rate can pretty much blow up your calculator. It doesn't have enough capacity to actually do that. Okay? And for instance, let's suppose that you type in the square root of 12.78. How exactly would they do that, right? How would they actually figure out what that answer is? So there's something called linear approximations, okay? So to give you an idea of what it does, first let me draw you a picture. Okay, suppose that we had an x and y axis, okay? I'm going to go ahead and draw the square root function, which you guys know is a hook or half of a sideways parabola. So this right here would be the square root of x. Okay, and let's say we wanted to figure out what the square root of 10 is, right? We're trying to figure out what that is right there. Okay, what is the square root of 10? Whatever the square root of 10 is. Okay, so what the calculator does at a very fast rate, and this is what we call series in BC, okay? The way we apply calculus here is you think about a certain value, okay? And I'll choose 9 because the square root of 9 is really close to the square root of 10, okay? So the square root of 9 is right here in this blue point. What we're going to do is we're going to go ahead and draw a tangent line right there, okay? So if you guys take a look, that green dot, I'll label this, is the actual value of the square root of 10. We don't exactly know what it is just yet, okay? Now, if you noticed, I'll put in a different color here. That tangent line, right where 10 is really close to that green dot. So what we're going to do is we're going to use that purple dot as our approximation to estimate what the square root of 10 is. Okay? And again, this is just an introduction to our approximations. How you guys get a little bit better with your approximations, you'll learn in Calculus BC. So if you zoom in enough, Now, this picture doesn't do it justice, but if you zoom in enough, this blue tangent line will overlap that square root function. If you zoom in close enough. So if you zoom in close enough, that approximation will be pretty close to the actual value. Okay? So here's what actually happens on the calculator, okay? We're going to go ahead and find the equation of that tangent line, which you guys are very familiar with. And then we're going to use that tangent line to approximate what the actual value is. And then we'll see how close we are, okay? Now, one thing that you guys have to understand first is how to draw tangent lines. And I covered this in a previous lesson. Let's say we have this graph here, okay? It has two types of concavity here, okay? Obviously, when it's a U shape, which I indicated in blue, it will be concave up. And then when it looks like an upside down N shape, it'll be concave down, okay? So the rule is when you draw your tangent lines have to be outside of the curve. And outside becomes a little bit arbitrary because it depends on the curvature. So for instance, you guys need to be really quick with drawing these, okay? If it's concave up, your tangent lines are below the curve when it's concave up, okay? But you'll notice that the moment it's concave down, the outside of the curve is actually top. Your tangent lines are above. Something to remember, okay? So tangents are above, okay? So how do you know when a tangent line is above or below a curve, right? And it depends solely on the concavity. So I'll say it one more time. Whenever your function is concave up, your tangent lines are going to be below that curve, okay? When your curve is concave down, your tangent lines are always going to be above the curve, okay? So if we see the line as an approximation, because we're trying to use the tangent line as an approximation right here, right? So if a tangent line is above the curve, above the actual value, then the tangent lines are actually, and you guys want to write this down, an over approximation. And when the tangent lines are below, it's an under approximation. And again, this is solely based on the concavity of your curve, okay? So there's a little cheat sheet for you guys, okay? So how do we actually do one? I'm actually going to model you guys something that you'll definitely see on Delta Math, but also on your AP exam, okay? So I encourage you guys to write this one problem down because that's all you'll really need. So take notes in detail here, okay? All right, so let f be the function given by f of x equals 2x to the 5/4 power. What is the approximation for f of 15.9 found by using the line tangent to the graph of f at x equals 16? Now, if you're curious, you can go ahead and use your calculator and try to graph 2x to the 5/4. Make sure that 5/4 is in the exponent. I'm going to go ahead and hit graph. You'll get something that kind of looks like, oh gosh, something like this, okay? Kind of looks linear, but it curves a little bit. Okay, so what's happening here is we're trying to find out what happens at x equals 16, which is somewhere beyond the graph because you'll probably have the default window in place here, okay? So here's what we're going to do. First, what we're going to do is we're going to try to make an equation of a tangent line. You guys can write this down with me, okay? So I'm going to have you guys pause the video here, but think about it. Remind yourselves, what two things do you need to make a line? Press play whenever you're ready. Yes, you are right, I hope. You only need a slope and a point. Okay, so what do they provide us here? They tell us that x equals 16. So I know that the x coordinate is 16. And we're missing a few things, the y coordinate and the slope, okay? So to find the point, you just plug it back into your function, f of x equals 2x to the 5/4. Okay, so f of 16 is just 2 times 16 to the 5/4 power. Okay? I mean, you could use a calculator here if you want, but you could do this by hand. The fourth root of 16, what number times itself 4 times will give you 16? That's going to be 2. Okay? So the fourth root of 16 is 2, and then we're going to raise that to the 5th power. 2 to the 5th power is 32 times a 2, which is 64. Okay? And again, you can use a calculator if you'd like, okay? But you should practice fractional exponents, okay? Okay, so we have a point. All we're missing is a slope. So here we go. So how do we find a slope again? Think about that before you continue on with this video. To find the slope, slope just means derivative. So here we go. Derivative is just f prime of x. So how do I take the derivative? It's going to be just the power rule here. So it would be 2 times 5/4 x to the 5/4 minus 1, which is 1/4. Make sure you get that before you move on, okay? Now this right here is just the general slope, but specifically we want to find the slope at 16. So this is 2 times 5/4 times 16 to the 1/4 power. Okay, so that's 2 times 5/4 times 16 to the 1/4 power. That's the fourth root. The fourth root of 16 is just 2. Okay, if you multiply all that out together, you should get 5. 5 represents our slope. Okay. So we have everything we need here. Let's go ahead and make a tangent line. So we have y minus 64 equals the slope 5 times x minus 16. Now, the only thing different with linear approximations is that, usually we leave it here, but we're going to use this tangent line. So what we're going to do is we're going to isolate the y here by adding 64 to both sides. So that's going to be y equals 5 times the quantity of x minus 16 plus the 64, and we'll leave it right here. This is your linear approximation. Okay? So there's a little insert right there for your tangent line. You're going to go ahead and write y equals 5. Whoa, that was really bad. Y equals 5 x minus 16 plus 64. I'm zooming in too much, okay? Okay, so now what we want to do is, they're asking you what is the approximation for f of 15.9. We're actually going to go ahead and use this linear approximation and find out what the y value comes out to when x is 15.9. So here we go. It's going to be y equals 5 times 15.9 minus 16 plus the 64, okay? Go ahead and pause here. Compute that on your calculator. I'm going to do the same right now. Okay, so you should get 63.5. Okay, hopefully I'm correct here. So our approximation, our guess for what happens at 15.9 is 63.5. Okay, so that's what you would be typing in for your delta math here, all right? Okay, now here's the tricky part. There's a lot of drop-down menus. When something happens, the second derivative is something, meaning the graph of f is something near the point of tangency, making the value on blank, under or over approximation. So I'm going to draw you guys a picture here, okay? How do we know that this approximation, this value that we got right here, how do we know that that was an over approximation or under approximation? So going back to this picture here, how do we know when it's an over approximation or under approximation? Pause and press play whenever you're ready here, okay? Whether it's over or under approximation, that depends on the concavity of your function. So we have to get a little bit more information here, okay? We have to know what the concavity is at this point. So how do we talk about concavity? Okay, we have to get to the second derivative. Second derivative talks everything about concavity and points of inflection, right? Okay, so here's what we do. We're going to get to our second derivative. So our first derivative is, if I reduce that, 5 halves x to the 1/4. I just got that right here, you guys, okay? But I simplified the 2 and the 4. Okay, so now that I have my first derivative, I'm going to go ahead and find the second derivative. Press play whenever you're ready, okay? But try this out on your own. Okay, so this is going to be 5 halves times 1/4 x to the negative 3/4. Okay, this comes out to 5/8 x to negative 3/4, which is the same thing as 5/8 x to the 3/4. If I fix that negative exponent, this is my second derivative. Okay. So remember, I'm trying to figure out if my answer that I got right here is an over or under approximation. So I have to know, well, at 15.9, was it concave up or concave down, right? So here's what I do. I'm going to go ahead and plug in 15.9, which is my x coordinate. Okay. 15.9 will give me 5/8 times 15.9 to the 3/4 power. Now, don't do that in your head, but just by analyzing this, 15.9 cubed will give you something positive, to the 4th root will give you something positive, times the 8 will give you something positive, and 5 divided by that will give you something positive as well. So we don't know what it is, but we do know that it's positive. Okay? So what that tells me is that when the second derivative is positive, then that implies that f is concave up. So if f is concave up, your tangent lines are going to be below it. And if it's below, it's going to be an under approximation. Okay? Think about that. Replay that a few times before you need to continue, okay? Okay, so here we go. So since 15.9, since 15.9 is positive, okay, a positive number, so we're going to select when x is greater than 0, okay? The second derivative came out what, right? We know that the second derivative came out positive, so you're going to select that, meaning that the graph of f is concave up near the point of tangency, making the value on under approximation. There you have it. Obviously, going into detail, it's going to take a little bit of time, but that's what you guys are looking at here. Replay this video as many times as you guys need to, okay? Now, if a function is concave up, then you know your second derivative is negative, meaning your tangent lines are going to be above it, meaning it's going to be an over approximation, okay? You guys will have a lot of opportunities to practice through Delta Math, so go ahead and get started there after this lesson, okay?